Good afternoon, everyone. This is Dr. Carlos Morillo. I work as an application scientist in JASCO Inc. Today, welcome to our first webinar about spectroscopy that is related to RAMAN and instrumentation. This is the first of a series of seminars that we are going to be presenting in the coming weeks. Today we have Dr. Burgess, James Burgess. I just want to do a brief introduction and then I'm going to pass to him to start his presentation. So Dr. James Burgess obtained his bachelor's degree in chemistry at the University of West Georgia, performing ultra-high vacuum and environmental chemistry research. Also, James earned a PhD in analytical chemistry at the University of Alabama for surface science and material research using infrared reflection absorption spectroscopy. In vacuum system, also Raman microscopy of ferromagnetic perovskites and fabrication and spectroscopy of carbon material. He also taught 2 years at the Georgia Southern University and worked as a postdoc in the National Research Council at the Naval Research Lab. At NRL, he was involved in the research of functionalization of graphene, including the first reported fully fluorinated graphene and functionalizing micromechanical resonators. Next, he was working as FTIR and Raman applications focusing cells using seminars, demonstration, and experimental design. He also has been awarded 2 patents, 5 research rewards, and 2 book chapters, 3 grants, and 12 manuscripts, with more than 1,500 citations, more than 40 plus posters and presentations. So now with you, I'm going to, now James is going to let us know about Raman, okay? So James, whenever you feel, please go ahead.
Hey, Carlos, can you switch over to me to where I can show my screen? There we go. Thank you, Carlos, for your introduction. So my name is James Burgess, and I'm going to be talking about Raman and theory and instrumentation. So first, about JASCO. So we were founded over 60 years ago by Yoshio Fujioka, Shinichiro Yamanaga, who actually shared the Nobel Prize with Richard Feynman. At JASCO, we have 6 PhD scientists, including 2 vibrational spectroscopists, which is Carlos and I. We have an extensive background and expertise in spectroscopy, including FTIR, Raman, electronic circular dichroism, and vibrational circular dichroism, IR microscopy, UV vis, and fluorimetry. And you'll see why our expertise in UV vis actually helps us with Raman microscopy when we talk about the instrumentation part. So I wanted to just start off with a few Raman examples. There's plenty of examples out here, but it just gives you a flavor of what could be done with Raman. So the first is using a macro accessory. Let me get a better cursor for you guys. So it's using a macro accessory to interrogate a vial containing a liquid. In this case, it's ethanol, and it can be matched with a library. Oh, sorry guys, that's weird. There it goes. It can also be used to look at polymorphs, and if you look, the CO3 peak is the same on both, while the modes, the vibrational modes of 285, 155 is indicative of calcite, and the mode at 210 is indicative of aragonite. So that's one of the common uses is polymorphs for Raman. Sorry, guys. Okay, so next is compositional mapping. So this is an example with some polymer beads on a glass slide. You can see the green matches with polystyrene and the red matches with PMMA. So this is useful for things like microplastics that you may find different plastics and want to identify them on a certain filter paper. It can also be used for stress and strain analysis. So this is a lithographed silicon on silicon. And as you can see, the edges, there is some difference in peak shifts. And also impregnated polymers are inorganics in a polymer matrix. So in this case, we have blue and green silicon and titanium oxide in this polymer. So let's talk about theory. Raman shifts are on the energy levels of mid-infrared, and we use ultraviolet, visible, and near-infrared to actually interrogate the samples to get the mid-infrared information. So from right to left, we have increasing energy, increasing frequency, and decreasing wavelength, and they're related. The energy is related by Planck's constant times the frequency, or Planck's constant times the speed of light divided by wavelength. So the typical infrared, if we look at the energy to go through different transitions, this is an electronic transition from E1 to the excited state. And this is a infrared transition from the ground state to the second vibrational state. When a laser hits a sample, it causes what's called, instead of the electronic state being promoted, it promotes it to the energy of the wavelength of the light being used. So 1064 is going to have a lower energy or lower energy than 785 or 532. Most of the time you have what's called elastic scattering. So elastic scattering, no energy is lost or gained by the photon hitting the sample. And this is called the Rayleigh line. Sometimes, however, the light, when it gets promoted and relaxes back down, it'll be promoted from the first excited vibrational state and relax down to the ground vibrational state. The difference in these energies gives you an energy of the magnitude of that vibrational state. And that would be the energy for the emitting photon is going to be the energy of the wavelength plus the energy of that vibrational state. And that will be anti-Stokes transitions. For Stokes transitions, it starts at the ground vibrational state, goes up to the virtual state created by the laser, and it relaxes back down to the excited vibrational state. Again, the difference between these two energies is the same as that difference of the transition for infrared. So Raman uses electronic transitions to measure the infrared levels. Sorry, guys, 1 second. There we go. There is a competing event, though. So you have Raleigh is the most probable scattering event, and then Raman is about 1 in a million. However, fluorescence is about 1 in 1,000. So this is a much greater probability, meaning greater density of states, meaning it can swamp out your signal. And we'll see an example of that later. What happens with fluorescence is when the electron is excited to the first excited electronic state, it will actually undergo an radiative transition to the ground vibrational state in the excited electronic state. This will then emit a photon that has a lower energy than the photon coming in. So you'll see this, since it's lower energy, you're going to see it in the Stokes transition stage, which is what we mostly look at in Raman in the field. So the Raman effect is 1,000 times less likely than the fluorescence, which is 1,000 times less likely than the Raleigh. So this is what a total spectra of Raman would look like. In the center, you have the Rayleigh line, which is the same energy as the incident photon, and then you have Stokes and anti-Stokes transitions that occur. As you notice, the Stokes is much higher than the anti-Stokes, and that is because you're more likely to see the electrons in the ground excited state being promoted than a higher excited state. And notice the difference between the Raman shift in wave numbers and the Raman shift in nanometers. A small change in nanometers can lead to a large change in Raman shift. When we talk about calibration later, it becomes important. So this is a spectra of cyclohexane, and it's both an IR spectra in transmission and a Raman spectra in scattering. So as you can see, the same peaks line up through each, but the intensities shift. That's because there's a difference in selection rules for the molecules. So infrared energy, when it hits a molecule, it excites the dipole moment, which causes a vibration. So the first selection rule the most important selection rule for Raman is that it has to have a dipole moment change throughout the transition. For Raman, the electron cloud is changed, which causes a transition, vibrational transition. So here we have a tight, small electron cloud around the molecule while it's compressed, while the oxygen and the carbon's compressed together. This is at equilibrium, and this is when they're stretched apart. So what happens here is that the polarizability, which is how easy is it to cause a transition, the polarizability here is a lot higher than the polarizability here. So if we chart this with the molecular position, so this is equilibrium, that's compressed, that's expanded. If we do a chart, we see that from the beginning of the vibration to the end, we actually get a change in the polarizability. So another example of IR and Raman modes is CO2. So CO2 is a linear molecule. Linear molecules are going to have 3n minus 5 number of vibrational modes. So the larger the molecule, the larger number of modes that you have available. So with the symmetric stretch, as you can see, it gets smaller, equilibrium larger. So you can imagine the dipole, the electron cloud around it is smaller here, larger here, and largest here. So you have a change in the polarizability across the vibration. So it's Raman active. However, the dipole moments cancel each other out from molecule to molecule. So that means there's no change in dipole moment, meaning it is not IR active. The asymmetric stretching, in which one oxygen is compressed while the other is elongated, then at equilibrium, and then the opposite oxygen is elongated, you can see that there is a change in dipole moment between the Q plus to Q minus. However, there's no change in the electron cloud. So that means that it's IR active. So let's look at bending, and I'm going to let you guys guess what you think is going to happen. I'll give you a couple of minutes, a couple of seconds. So the question is it going to be IR active, and is it going to be Raman active? So it turns out to be IR active. The reason it's IR active and not Raman active is that the first transition the electron cloud around the first transition position is going to be the same as the final position. So there's no net change in polarizability. The dipole moment, however, one is formed when it's in the bending mode, relaxed, there's no dipole moment, and then there's one in the final mode. So it's IR active. So as we saw with the cyclohexane, there were many different vibrational modes there. So again, it goes to that 3n minus 6. The reason they are all at different places is because each bond is going to have a different energy related to the spring constant and molecular mass. So if we increase the spring constant by having higher and higher order bonds, we increase the energy of transition from 1400 inverse centimeters to 2200 inverse centimeters. The mass, as we increase mass, we actually decrease the energy. So each molecule is going to have its own vibrational modes, and those can be predicted by looking at tables. So the oxygen hydrogen stretches all happen since we have a very light mode and it's a very weak bond, all happen around 3500 down to 3200. The CH bonds happen around 3000. And then the other bonds like alkane happens at 26, and the C triple bond N happens about 2100. So they give similar information, again, as we saw with the cyclohexane, they give similar information, and the question becomes, when do you use Raman over IR? So for organic molecules, IR and Raman are pretty much equivalent. They see the same modes for the most part, especially the larger the molecule, the more modes they're going to share because the symmetry starts to break down. However, I like IR for organic molecules because the CH region is usually a little more intense. For inorganic compounds, IR will see some of the modes, and it can actually get down to 50 wave numbers, but it requires special equipment, and the Raman inherently does better at the lower wave numbers, so which is where most of the inorganic modes occur. Aqueous samples for IR, water is a very highly absorbing compound, so it's really difficult to get good peaks because it drowns out all the signal. Raman, however, is very insensitive to water, so it's very good for aqueous systems. So the only down part is that its limited detection is not as good as the limited detection as IR. Microscopy, I would put them both on the same pedestal. There's some examples where Raman is better for microscopy, such as Raman can do depth profiling and IR cannot. And also with fluorophores, so a compound that's going to fluoresce, you can use IR, is insensitive, totally insensitive to fluorescence. And in Raman, it's fairly difficult, and I will show you one way later how you can get around it. So the Raman optical configuration, let's talk about the guts of the hardware. So this is a cartoon schematic of the Raman configuration for a bench. So you have, and each of these I'll discuss in turn. So the excitation laser acts as the source for the Raman process. The objective focuses down the beam onto the sample. It's reflected back up and through a rejection filter into a monochromator. And the monochromator consists of a grating and a detector. So this is a cutaway. This is a very old style laser, but there's a cutaway of a ruby laser with a quartz flash bulb, two mirrors, one that reflects totally, the one that reflects partially, a reflecting aluminum cylinder around it, and electric circuit wire. Really the main importance is the flash bulb, the lasing material, and the mirrors. So the three stages are pumping, where light of different frequencies gets emitted from the quartz lamp into the sample, and then it causes excitation, and the excitation's at different wavelengths. So there's fluorescence down from to the band gap between the first and second electronic state, so that all the electrons have the same energy. And then it undergoes spontaneous emission, where those excited electrons then relax back down and emit photons. But those photons are in all directions and have all different polarizations. With stimulated emission, those photons that are released cause an excitation, and then during that relaxation phase is where you get the coherent electrons that will bounce off the mirrors until they're at high enough energy that they go through the partially reflecting mirror. That's the older style lasers. The new ones are diode pumped. So instead of this quartz flash tube, you have a diode laser. So it actually is more efficient than the quartz lamp style. So laser options. So there's options all the way from the UV all the way to the near IR. These lasers are available off the shelf to be put in, pretty easy to get. One, and each has its own drawback and advantages. The UV lasers have the highest intensity, but they also tend to burn the samples. The mid-range are really good lasers to use. They work fine for day-to-day operations and samples. Like the very bulk of Raman uses these laser wavelengths. The 785 and 1064 are good for fluorescence, which I'm going to talk about now. So I've been harping on fluorescence throughout this talk just because that's the most common barrier to doing Raman on a sample is when it fluoresces. So in this case, we have 4 different lasers, 532, 633, 785, and 1064. As you can see, there's fluorescence in the sample that as you increase the wavelength, that fluorescence disappears all the way down to where it's non-existent. The downside to the 1064 laser is that it's really low power, and also you have to have a special detector that's just for 1064. However, a better choice for this sample would be 785, because even though there is some fluorescence, you have a lot of signal, and this fluorescence could actually be taken out through an algorithm in the program. So choosing a laser, there's a lot of give and take. It's a good idea to always have a sample ran of yours at the different wavelengths before you buy it. And I do want to talk about laser safety. When I first started at Naval Research Lab, I was going to be working with lasers, and they actually took a retinal image, which I didn't understand at first until I came across this case study where a student, an undergraduate student at Los Alamos, actually burned her retina because she was accidentally exposed to YAG laser. And YAG lasers are at 1064, so they don't actually, you can't see the laser because your limit of vision is 390 to 700 nanometers. So she had no way of knowing whether the light was on, what the beam path was of the laser, and since she was working with non-visible light, her pupils were dilated, which actually allows more light to come in and damage the retina. Without a safety enclosure, these lasers are all class 3B. So they're not compliant independently. You have to have things like laser training for everyone that goes into the lab, not just the user. Special signage for the laboratory telling if the laser's on or off, and special laser safety goggles, again, for everybody in the lab. And if you've ever worked with laser safety goggles, it's not fun. With a safety enclosure, it's class 1. So it's around the same as a scanning machine at a checkout. So with the laser safety enclosure, you have safety interlocks. So if the compartment is open, the lasers are going to be shuttered. Another safety feature of ours is we actually, when the decision was made not to use optics, to use binoculars like you see in a regular microscope, part of that decision was actually we didn't want any kind of stray light coming through the eyepiece to someone. So there's a lot to be said about laser safety. So again, the shift, if we look at the Raman shift versus the wave numbers, a small shift, a 0.1 nanometer shift is 4 wave numbers. So it's really, really important to know the actual energy of the laser coming in. So the one way to check is using a polypropylene, silicon, or diamond standard. Those all have really sharp peaks that have a well-defined wave number, and those are good for a routine sanity check. Am I saying what I think I'm saying? The better way, we all know to take a calibration, you need at least 3 data points. For me, I prefer 5. So if you're wanting to do a true calibration on the instrument, you need 3 to 5 data points. And one way to do that is internal neon lamp, which has multiple spectral lines that are all well-defined, and they're all very narrow. So we talked about the lasers. We're going to move on to the objective lens and the spot on the sample. So there's a lot of different objectives that are on the market. So we use regular Olympus objectives. However, one of the biggest challenges is that the light coming from the sample, we need as much as possible because it's very weakly scattering. So the ones that we need have something called a high NA. NA is numerical aperture, and it's related to this angle, the angle of the cone hitting the sample. So for a long working distance, a short working distance objective is going to have a wider cone, therefore a larger angle here than a long working distance objective. And one of the things that this working distance, the numerical aperture affects is the beam waist. So it's basically a cylinder of where the spot is on the sample. So for the peak width, it's related to wavelength divided by NA. So the higher the NA, the better. The higher the NA, the smaller the spot. For the wavelength, the smaller the wavelength, so in this case, these numbers are all done with the 532. The smaller the wavelength, the smaller the spot size. So what you want for really good spatial resolution is a short wavelength laser with a high NA. And if we're doing a depth profile, like I showed earlier, if we're doing a depth profile, you also want the high NA and a small wavelength. All right, so we're going to travel down through now to rejection filters. So rejection filters block the excitation laser. The reason we want to block the excitation laser is that these detectors are all tuned to very, very weak signal, and the laser line is a very, very, very strong signal. So if it's not properly filtered, then it will destroy your detector, which is a very costly mistake. So it's blocking just one wavelength of light. So so each laser line you would have on an instrument requires a different filter. And there's three main choices in filter types. The first is the edge filter. This is the workhorse. This is what you use 9 times out of 10. It's good for Stokes transitions, and it's got a high intensity for the throughput of 92% and a fairly reasonable wave number cutoff at 100 wave numbers. There's not a lot that happens below 100. However, sometimes there are. So radial breathing modes in carbon nanotubes is an example of where you want at least 50 wave number cutoff to see the modes. And the downside is that it's got a lower reflectivity. And finally, the notch filter, it just filters out the laser line and allows you to see both the Stokes and the anti-Stokes transition. These have a lower lower transmission. It's about on par with the low E, and it has a high wave number cutoff of 150 wave numbers, which is not crippling, but it still needs to be addressed. The reason you may want anti-Stokes is that if you do have fluorescence problem and you don't want to buy another laser line, you can get and detector, you can actually use a notch filter to look at the anti-Stokes, which are impervious to fluorescence. You can look at the lower energy. The downside is that you can see the signal is even weaker here. So the other, the filter placement is also important. So in our situation, in our system, we have a notch filter in the beam line after the beam splitter, which means that the visible light that we're seeing with our camera is the same path as the laser line is. If you have a notch filter, it can actually cause that spot to be at a different point in the sample. So an example of our setup, you can actually see the laser line on the visible image, which is good because when you're mapping, that's the whole point. Or when you're, trying to find a piece of particulate on a sample, you want to know that your laser beam and your visual beam are also in alignment. From there, it goes into the monochromator. The monochromator we use, I believe everybody else uses, is the Zerny-Turner type. And all that means is that it's using two focusing mirrors. One is a collimating mirror, and the other is a focusing mirror. And the collimating mirror takes the light from the experimental setup, reflects off a grating and into a detector. So how does a grating work? So I think this is skipped over a lot, and it's really important, and it actually will answer a lot of questions later on down the line when you're looking at different gratings. So how a grating works. So if you have a broadband light hitting a sample, it reflects at different angles. It has a reflection angle, and each angle is dependent. It gives each wavelength reflects off at a different angle. So you have a broadband coming off being separated by different angles of angles coming off the sample. Also, D is related to the wavelengths coming off. So the smaller the D, the smaller number of wavelengths are coming off, and this D is reflected in the grooves per millimeter. So light's coming off and it's being separated and it fans out from the grating. So the further away your detector is, the greater that separation is. And our examples are from our different instruments. It's NRS 4500 to NRS 7500, all have different focal lengths, which is the big difference between the systems. And our resolutions actually reflect this. So it goes from 2 to 1 to 0.7 as we go up. Another thing with gratings is that the higher the number of grooves per millimeter, the lower your distance between the grooves in the grating. So that means the higher the number of grooves per millimeter, the better the separation, but the smaller the wavelength range you're going to look at. With the 600 grooves per millimeter, it's a lower energy. It's a greater span of frequencies, but a lower resolution. This can be illustrated here. So if you look at the top line, is the 300 grooves per millimeter grating, and it has a very long, a very wide Raman range. And as you go 600, 1200 to 2400, it gets smaller and smaller and smaller. And if you look at the exploded view of just this low wave number region, what you get is a higher resolution as you go down. So it's always best to have at minimum 2 gratings per laser matched so that you can do survey scans to get a quick reading. Let's say you want to make sure you're hitting the area that you want to hit, the molecule you want to hit. You can look at it in a broad view, but if you're wanting to look at subtle differences such as stress or strain or polymorphs or anything like that, you may want to have a higher resolution. Now, the position of the position of the grating is really important to know, and the easiest way to do it, or the one way to do it, is to have a LED bulb and having coating. It goes through different slits, and those all mean it's at a different place in the wheel. It goes through a fixed slit into a detection element. For a lot of manufacturers, there's just one, and then one fixed slit and one detection element, and you only know when the grating goes all the way around. So each time you stop a measurement, you have to go all the way around in the grating, which can take some time. With our design, we have, and this cartoon has 1, 2, 3, and then there's 4 behind it. So you know 4 places in that travel. And the reason you want to know all this is because you have to have wave number repeatability. And the better you have this down, the better the repeatability will be. All right, so let's talk about detectors for a minute. This is a picture of a CCD device. So it's charge coupled device. These are found in, nice CCD cameras. Some use a silicon based, but the charge coupled is much better. This works for every laser except for 1064. 1064 uses an N-gas array, and it covers the near IR wavelengths converts near IR wavelengths to electronic signal. So if you're wanting to work with both visible and the 1064, you'd have to have 2 different detectors. The EMCCD multiplies the signal from the CCD detector. And this is an example of the EMCCD. So a normal CCD camera bends its information, and this is the vertical transfer. There's a serial transfer over here. But the vertical data transfer comes out, and it's just one electron going in, 1 electron coming out. For EMCCD, it goes into the register, and then it gets multiplied with using special materials to go from 1 electron in to many electrons out. And what it means is that you can take a really noisy sample, and in the same number of scans, you get a much clearer measurement. So just to summarize, Raman uses electronic light to get vibrational energy. The result of the change in polarizability of a molecule. Each has different selection rules with the polarizability and the dipole moment, which gives differences in the spectra. The laser is the Raman source. There's tons of stuff on the market to choose from. It's always best to talk to someone before you make a decision, run some samples. Rejection filters remove the laser line from the beam path. And gratings determine the wavelength range and spectral resolution. And detectors convert photons into readable electronic signals. So I thank you for listening to me this afternoon. And I just want to bring up, Carlos mentioned that there's upcoming webinars. So we're going to do vibrational circular dichroism, FTIR theory, instrumentation and techniques, circular dichroism, FTIR microscopy, Raman microscopy and imaging. We have several ebooks that are available for download off our website. We've got Raman tips and tricks, fluorescence, FTIR, and we have a confocal Raman microscopy theory page. We have some more theory pages as well. And we also have a knowledge base, which is a pretty good resource if you want to find some real world applications that have been made by our customers. All right, thank you. Off to you, Carlos.
Okay, thank you, James, for
Thanks.
that excellent presentation. So now we are open for questions.
Hey,
but
Carlos,
I can see that there are, yes. Well, there are questions here that I can answer. For example, we have a question from Iran, and he's asking if we are able to have the presentation afterwards. Of course, you are going to have access to, you are going to have a copy of the presentation, also access to the recorded webinar. If you have questions, you can write it in the questions box. But at the same time, if you have any question, I'm going to give you access to audio. So now, if you have a question, you can ask. Okay, yes. Yeah, if you have questions, you can, I think that you have access to unmute yourself also. Okay. Okay, we have a question from Joseph. Nini, Joseph, if you want, you can make your question now. No, I can read it here. It says, James, are you back?
Yes.
Okay, so the question is, does the Raman depth profiling measurement come with the Raman microscopes?
Yes, you can get it with it.
Yes, yeah, that's the answer. Like, yeah, it comes with the depth profiling because the Raman microscopes are confocal, so you will have you will be able to do a mapping not only in X and Y axis, but also in Z, that is the penetration. We have another question from Amal, and he says, what is recommended for polymer composite?
Are you wanting to see like the different parts, like how thick are the layers?
Yeah. Okay, I'm going to unmute Amal. If you want to make the question, you can do it now. Amal, if you have a microphone, you can make the question now. I think you have audio now.
Well, so Raman can be used for composites. You can, if they're thin enough, you can do a depth profile. Otherwise, you can actually cut it and do a cross section. And depending on how thick each layer is, will drive your decision on which laser line to use.
Yeah. Actually, if Amal wrote his question, and he say it's just to study the interaction between the conjugated polymer and glassine.
Glass?
Conjugated polymer and graphene.
Graphene. Oh, yeah. Yeah, you should be able to see that. Graphene will show up really well.
Yeah, exactly. Amal, graphene is going to show really well using a Raman instrument. Okay, we have several questions. We have a question from Tatiana Dindikova. Is there a way to quantify the amount of stress and strain?
Yes, there's actually there's equations. I mean, it depends on the sample how easy the equations are, but you can actually tease out a good deal when you're looking at stress and strain. It's you have to know how do I put it? Trying to remember the equations. I can't remember the equations off the top of my head, but you can quantify how much there is, especially if you know the beginning and the end of the strain and the stress. So if you know it before it breaks, and then you can actually use that to make a calibration curve, basically. You know, like if it shifts 5 wave numbers, then you know it's shifted 60% of what you expect.
Yeah, that's correct. And just adding to what just James mentioning, you can have also correlation between of the stress applied to the sample and the shifting in the wave numbers. Actually, we have a nice application node using one of our instruments, the NRS 7600, that have the highest resolution. You can work, especially for semiconductors, you can find the correlation between the shifting in the Raman peaks and the residual stresses in your samples. But it's something that I have seen, especially for semiconductor materials. I'm checking for more questions. Well, I think this question is really good. I don't know if I don't have the answer. Maybe James, he said that the Raman technique, it would be similar to SEM backscattering.
I think the backscattering, aren't you looking at electrons, not photons?
Yes, exactly.
Yeah.
It's a totally different principle.
Yeah, so it's pretty different. Yeah. It's type of scattering, but it's photon.
There is another question from Wojun 1. It says, like, can you make any comment on using Raman microscope on organic compounds?
You read that again?
Can you make any comment on using Raman microscope on organic compounds, organic materials?
Yeah, I mean, it's a good technique. So as far as, are we talking about organic, living organic, or organic chemistry organic?
Organic is just a general question. It didn't.
Okay. Yeah, so most of the examples I showed were organic molecules. So it's going to have similar vibrational modes as IR most of the time. You may have some more intense peaks than you would see in IR, and some IR intense peaks you wouldn't see. So as far as organic molecules go, it's a pretty standard instrument. It goes along well with FTIR.
Okay.
I mean, can you add anything, Carlos?
Well, organic materials are the tools that you can use to study or characterize organic materials. The first options are going to be vibrational, molecular vibrational techniques. So Raman, for excellence, is one of them. But I would say that Raman, you can enhance a little bit your analysis, because you can analyze organic materials and also some inorganic materials. So that is one of the strengths of using the technique like Raman. There is a question from Jose Sanchez, and he said, what environmental factors can affect the analysis? Jose, can you make another question and try to be more specific? And I'm going back to you when you specify what is exactly the environmental and what analysis, what samples are you referring to? We have a question from Michael Phillips. He said, like, how often does the instrument need to be calibrated? The instrument, there are different calibrations that you can do to the instrument, especially we can calibrate both the laser, we can have the laser alignment, also the Raman path alignment. Especially me, I can check the wave number. I can do it every time that I do the measurement, but the variations that I see, they are minimal. They are within the resolution of the instrument. But the Raman path alignment that involves the whole optics inside the instrument, that is something that you can do once a month, or even you can do it like every 2 months. But it depends on your sample and the testing that you're doing. But actually, you have the flexibility with these instruments to do an automated calibration, also do it by yourself. As James was mentioning, we have different standard samples to calibrate that comes with the instrument. We have silicon, polypropylene, polystyrene, and actually we have inside halogen lamp that you can do, and I really like that option because you can do the calibration without opening the instrument. So we have different options to calibrate, but actually the instrument is very, very stable. We have another question with Jack Liu. It's any application examples related to diamond and graphite, especially for microscopy and imaging. Jack, we have different application notes, and we can reach out to you later to send you these applications. But as we were mentioning before, Raman is the tool to go when you are measuring carbon materials. So especially diamond and graphite, there are some materials that easily they are going to have a very nice Raman signal. So you can easily study, and of course you can measure the Raman spectrum, and at the same time you can do your imaging and mapping. Okay, James, we have a question about humidity and dust that affect the performance of the analysis.
Well, it's an enclosed instrument, so you really shouldn't have a lot of trouble with dust. As far as humidity, I'm not sure. Do you know the range, Carlos, off the top of your head?
I don't have it from the top of my head, but
I mean, I'd imagine
it's something that I can definitely check and reply that question offline to Jose.
Yeah, I wouldn't worry about the dust, but humidity, I mean, there's not a lot of optics in there that get hurt. It's not like IR where you have to worry about KBR.
We have another question from Heidi Krekel, and to say if we have used an instrument that have 2 laser stimulated Raman systems. I don't know. Our instrument use 1 laser at the time. I don't know if this is something that I can ask on. Sorry.
Is it simultaneous?
That is what I would like to know. Hey, Heidi, if you are listening, you're still in the forum, please. Could you please answer that question? If the 2 laser systems are used simultaneously or they are used at different time, because our system, they can have different lasers. At least the 4500 series, it can have 3 different lasers mounted. Of course, you can use it at different times. But Heidi, if you want, we can continue this conversation offline, because I can see that your question, you have several questions.
Yeah, that may be better, just a phone call.
Yeah, she just replied that that a pump and a probe laser is used simultaneously. Okay. Yeah, we can talk with Heidi offline. I think that those are the whole questions. There's one more question, but I think this is really long. Maya, I'm reading your question, and I will contact you afterwards.
All right.
I think that is everything that we have. We have another question about, final question about installation of the equipment, but I'm going to let for installation. Usually, our service engineers are the ones that do the installation. So if you send me the question, Jose, I would be happy to answer or give it to the engineer team, the service engineer team. Well, I think it's almost 3. It's 3 p.m. I just want to say thank you very much to all attendees. Thank you for your questions. They are really good. And for those that they are longer questions, I would be happy to continue the conversation offline. Heidi and Maya, we are going to contact you soon. You have, I think you have my email, because you were getting the updates and the invitation from my JASCO Inc. email, so you can reply today if you have any questions. And also, I think you have email from James, and we are just happy to continue these webinars. For those, I'm just getting a message from our marketing team. They are telling me that please follow us in LinkedIn. And for those that they were on LinkedIn and saw that for this webinar is going to be a draw and drawing, and there is some prizes for some of the person that attended today. I believe it's a Yeti, so I think it's a very nice souvenir from us, from JASCO, and a winner is going to be selected for those that they subscribe to this seminar. And soon somebody from our marketing team is going to contact you if you are the winner. So with that, you will get it in the email. So with that, I just would like to say again, thank you. And we are going to email you again for the coming webinars.
Right,
thank you very much to everyone.
All right, thank you.